Hello. Today we're going to talk about the rhombus, rectangle, and square. I expect you're very familiar with the rectangle and square. The rhombus, on the other hand, well, until you took this course, you probably thought the rhombus was extinct. Nope. There's still lots of them around. Hope I spelled it right. Yeah, it's spelled right. What the heck is a rhombus? I don't know why it's called a rhombus, but I do know what it means. As I'm sure you know, a square has 4 congruent sides. Every side has the same length. Well, a rhombus is exactly the same thing, except for one difference. We got right angles here in this square, and that's a requirement for a square. 4 right angles. A rhombus? No. Just has to have 4 congruent sides. It can have angles that are less than 90 degrees and then more than 90 degrees. They still have to add up to 360. It's still a quadrilateral. But the angles as you go around do not have to all equal 90 degrees. So, from the definition of this, 4 congruent sides, well, you can see that a square would actually fit the definition of a rhombus, but not the other way around. In other words, a square is actually a very special rhombus, and it's the one most people are familiar with. Rectangle, oh, it's pretty simple. Just any parallelogram with 4 right angles in it. Now, we've defined a parallelogram as a parallelogram with 4 congruent sides. Can we go the other way? If we have something with 4 congruent sides, is it necessarily a rhombus? And the answer is yes, it would be. Because the only other condition it has to fit to be a rhombus is parallelogram. A rhombus is a parallelogram with 4 equal sides, or 4 congruent sides. If we know we have 4 congruent sides, we immediately know that we have a parallelogram. Why is that? Well, because of a previous theorem, which told us that if opposite sides of a quadrilateral are congruent, then we have a parallelogram. So this side is congruent to this side, and this side is congruent to this side. The fact that they're all congruent to each other is kind of irrelevant for showing that it's a parallelogram. Rectangle works the same way. If you find a quadrilateral with 4 right angles, then it has to be at least a rectangle. Remember, a square qualifies as a rectangle. It's got 4 right angles. It qualifies as a rhombus. It's a special case of each. But for a rectangle, it goes both ways. A rectangle is a parallelogram with 4 right angles. On the other hand, if we have a quadrilateral with 4 right angles, then we know we have at least a rectangle. We might have a square, but we at least have a rectangle. And for a square, well, as I said, it qualifies as a rhombus and a rectangle. And in fact, if you have something which you can define as both a rhombus and a rectangle, that is a square. So if you wanted to prove something was a square, one way to do it might be to prove it as both a rhombus and a rectangle, in which case it must be a square. It's another interesting property of a rhombus is that the diagonals are perpendicular. For a square, they would be perpendicular and congruent. But for a rhombus, they're not going to be congruent because obviously we kind of smashed it. It's like we took a square and smashed it down a little bit, but we kept the side lengths all the same. Well, obviously this diagonal is much longer than this one, but they still meet at a right angle. Why would it be true that these diagonals meet at a right angle? Well, it's easy to show. It's easy to see the sense of it. First off, we have that these two sides are congruent because it's a rhombus. Now, if we just take the section of the diagonal from here to here, remember, for any parallelogram, the diagonals bisect each other. So we also know that this half of the diagonal is congruent to, I should say, this segment. In other words, MC is the same as MA. They're congruent because this diagonal intersects at the midpoint. They both do. And this line, of course, is congruent to, this segment is congruent to itself. So by the side theorem, these two triangles right next to each other are congruent. All we have to do is match up the parts now. For instance, this side is congruent to this side, so this angle is congruent to this angle. Remember, I drew that 90-degree in there when I was telling you. Now I'm proving it, so I probably shouldn't have that in there because technically we don't know that yet. Okay, that's gone. All we know is that these two triangles are congruent. But if we start matching up parts, this angle is congruent to this angle is congruent to this angle, and the important part is this angle is congruent to this angle. But these two form a linear pair. And we have two equal angles which add up to 180, which means that they are in fact both 90 degrees. And if this one intersects at a right angle, then this over here is a right angle also. And they're right angles all the way around. That comes from two basic things. We just had to show that these two adjacent triangles, which were created by half of the diagonal here, they're congruent. And a big reason for that is the fact that they intersect at the midpoint. So since they intersect at the midpoint, that helps us show that these two triangles are congruent, which then leads pretty directly to the fact that this straight angle is broken up into two equal angles. So they're both 90 degrees. Pretty simple. It's also true that these diagonals bisect the angles inside the rhombus. Why would that be true? It kind of looks like that's what would happen, doesn't it? How do we show that it's definitely true? Well, that's pretty simple. We do the same thing we did last time, really. Except that we're going to show that this triangle here is congruent to this triangle. Yeah, it's pretty easy. This line is congruent to itself. These two sides are congruent. Well, but for these triangles, now that we know this is 90 degrees, we have a leg and a hypotenuse that are congruent, so we could stop right there. We could use our side because a right triangle is still a triangle, but we don't have to go that far because right triangles are even easier to prove congruence and similarity too, for that matter, but especially congruence. So if these two right triangles are congruent, their angles are congruent. This angle corresponds to this angle, but that's not the one we're concerned with right now. This angle corresponds to this angle, and this angle here is congruent to this angle. So, well, if the angles on each side of the ray, or in this case a segment, are congruent, then by definition this is a bisector. And all we had to do was pretty much what we did last time, just show that these two triangles are congruent. Once we do that, we have that these two angles are equal, and this must be a bisector. And we can do exactly the same thing here. We can easily show that these two triangles are congruent, these two angles are congruent, and therefore this is a bisector. That's pretty simple. Over here, we have another rule about rectangles. A parallelogram is a rectangle if these two diagonals are congruent. In other words, the fact that these two diagonals are congruent implies that all the corners are right angles. Interesting idea. Let's see what happens. Oh, how do we know that the diagonals on a rectangle are congruent? It's actually pretty easy. What we do is consider the triangle formed by this diagonal and these two sides of the rectangle. In other words, let's use a different color. Now this part that I've shaded in blue here, this corresponds to this triangle down here, right triangle. And this part here I shaded in black, that corresponds to this triangle here. See, ABD, ABD, and here we have ACD, ACD. Why would I do that? Well, the hypotenuse of this right triangle is this diagonal here, and the hypotenuse of this right triangle is this hypotenuse here. If I can show that these two right triangles are congruent, I can directly follows that the two hypotenuses are congruent. Well, because it's a rectangle, this side is congruent to this side. Well, pardon me, because it's a parallelogram, this side is congruent to this side. Remember, in a parallelogram, opposite sides are congruent. So that corresponds to BA here and CD. Well, here's BA and here's CD. They're congruent. Okay. And over here, AD does double duty. It's a leg of each right triangle, and of course congruent to itself. So there we are. We've got two congruent legs in a right triangle. That means the two right triangles are congruent and their hypotenuses have to be the same length. Pretty simple. That's the basis for most of these proofs. Usually when you're with all this stuff with the rhombuses and the rectangles, most of the time the quickest route to demonstrate the truth of any of these properties is to find a way to break up your parallelogram into congruent triangles. Once you've got that, it's easy to show that all kinds of things are equal to all kinds of other equal things. So, as a general rule for stuff like this, start looking for congruent triangles and see if they'll do you any good. That's very often the right way to get through these. Well, looks like my old friends Inseam and Fleabite are taking a shot at geometry again. And of course they got it all wrong. They tell us that this is a rectangle. They give us algebraic expressions for these two adjacent angles, and then since the adjacent angles of a diagonal are equal, wait a minute, how do we know the adjacent angles are equal? In a rhombus, the diagonals bisect the opposite angles, but a rectangle is not a rhombus. So this is no good. What do we know about a rectangle that would allow us to solve this problem? This is a right angle. That's from the definition of rectangle. That means these two add up to 90 degrees. So what he should have written was 7x, or this was probably a group effort, plus 3x plus 14 equals 90. And then we can solve this problem, which they didn't actually ask us to do, but what the heck, it's 10x, pardon me, 10x and it looks like x equals 8. Subtract 10, that's 80, divided by 10 would be 8. But the basic problem was this. Should never have written that. You should have written this plus this equals 90. And then you can solve for x. Well, for this one they give us the length of the diagonals of a rhombus. Now, what do we remember about the diagonals of a rhombus? Well, they definitely aren't congruent. They just told us that they're 6 and 8 inches. But they intersect at a right angle, don't they? They also intersect at the midpoints, meaning that they break each other up into two congruent segments. So the long diagonal is 4 inches and 4 inches. The short diagonal is 3 inches and 3 inches. But this is a right angle. Then this would be the hypotenuse. The hypotenuse of what? A 3-4 right triangle. So we don't even have to do any calculating. This is one of the ones that we just keep in that table in our head and don't even have to calculate it. Well, it's a rhombus. They told us it's a rhombus, so every side is the same. So if they're all of length 5 and we got 4 of them, the perimeter must be 20. 4 times 5. See, they made life kind of easy. By making it 6 and 8, that meant that they were divided up into a 3, 4, 5 triangle. However, the problem would only be a little bit longer if this were 6.7 instead of 4, and this were 3.9 instead of 3. You can still do it. You just square both of them, add them up, take the square root, and you'll have this. And once you got this, you're done because they're all congruent. So you only ever have to figure out one of these sides anyway with the rhombus, and then multiply by 4 and you got the perimeter. They just gave us easy numbers. Didn't even need a calculator for this one. Well, in this problem we're given that these two triangles are similar, and then we're given the two diagonals. Do the diagonals follow exactly the same similarity ratio as the rectangles? I think we may have already proven that they do, but suppose we hadn't. What's the big deal? You can always just sit down and work it out yourself really fast. I mean, what is the diagonal? Well, this is a right angle, so the length of the diagonal must be this squared plus this squared. So if we call this, say, L, and call this length M, the diagonal for our similar rectangle is going to be K times L, that's what Fj is, and then K times M. In other words, K times this length, and then K times this length. And that'll give us our new enlarged but similar rectangle. What would this new diagonal be? Well, it would be k times L, that's this leg, plus k times M. We square both of them. Well, that's going to give us k squared times L squared plus k squared times M squared. We can use our distributive property and pull it out and write k squared times the sum of L squared plus M squared. Well, if we take the square root in order to get this actual hypotenuse, what do we get? Square root of k squared is just k, and, pardon me, this is supposed to be L squared plus M squared. This right here is the original diagonal, or you could say the hypotenuse of this right triangle here. And our new diagonal is exactly the scale factor times the old diagonal, which means the diagonals follow exactly the same scale as the sides. We know that the scale for the two diagonals, this one went from 5 to 10, so it doubled. So this one would double. And there's 8 over there. And the answer would be 8. This over here, this wasn't really necessary to the problem. It's just a quick, easy way to remind yourself that the diagonals change exactly the same way the sides do. If you use a transformation to create a similar triangle, pardon me, a similar rectangle, where the sides are exactly double the original rectangle, then the diagonal will also be exactly double. That would be a good guess, but it wouldn't have to be true. It just turns out that it definitely is. Now here's one where they'd like us to find angle ADC. That's this whole angle here. Well, if we knew this angle, that'd be easy. Suppose if we knew this angle, we could probably do it too. How? Well, remember, all these angles have to add up to 360. Also, this is a rhombus. We got these little marks here to show that all these sides are congruent, so we have a rhombus. So they sure don't look like 90-degree angles. It doesn't look like we have a square, but that's irrelevant. As long as we know we have a rhombus, we can use all the properties of a rhombus. One property of a rhombus is that the diagonals bisect the opposite angles, which means this angle must be 2 times 53, which would be 106. Well, this angle is also 106. So multiply that by 2, and we get 212. So these two angles together account for 212 degrees. Now we have to subtract that from 360. I get 148. And what's 148 divided by 2? .74. So this whole angle here, that's 106. You double it, you get 212. Means there's 148 degrees left over. So remember, opposite angles are congruent, so we just take that 148, divide by 2, and get 74. And we could put a 74 in here. Boom. And okay, that was a pretty easy problem. Most of these problems, you're just going to have to keep in mind that for a rhombus, the diagonals are angle bisectors. It's not true for a rectangle, but it's true for a rhombus. And don't forget that a square is also a rhombus, so it shares the properties of a rhombus. And here's one where we're given our rectangle. We know it's a rectangle because opposite sides are congruent and we've got 90-degree angles all the way around. Remember, if you draw these two in as 90, they all have to be 90. The question is, what is angle QPR? Well, these are vertical angles. This is a vertical angle pair, so these two angles are congruent, this angle and this angle here. I only mention it because we are given one angle, and it's down here. Well, these diagonals form an upper triangle and a lower triangle. They're kind of flipped versions of each other. Well, at least I think they are. We haven't proven that they're congruent yet. We may not have to prove that they're congruent. That's one way to do it, but what about our properties of diagonals for rectangles? Not only do they intersect at the midpoints, they break each other up into equal segments, but the diagonals themselves are congruent. So QS is congruent to TR. So half of TR is the same as half of QS, which means that all of these are congruent. Well, I guess I should use 3 hash marks. I don't mean to imply that they're congruent to any of the sides, just to each other. Well, if these sections are all congruent, that means we have an isosceles triangle right down here. Well, what do we know about isosceles triangles? The base angles are congruent. What else do we know about triangles? Well, the angles have to add up to 180 degrees. So we've got two 34-degree angles, that's 68. What's left over would give us this angle here. That's 112. But that's not what they asked for. They asked for this one up here. However, this is the other half of a congruent vertical pair, so it has to be equal to this one down here. In other words, TPS is congruent to QPR. So the 112 is also the measure of this one. Now here they're asking us to classify this. Well, it's at least a quadrilateral. I say that right off the bat. We have 4 sides for sure. At least that's the way I would connect the dots. Actually, you could say that we had 2 triangles. But the way they drew this in here, I think they're trying to say that we have a parallelogram, perhaps. Who cares? Step 1, at least the first thing I would do, is see if these are right angles. You could do that. Or we could use our properties of diagonals and compare them. For instance, if they are congruent, then we must have a rectangle. If they intersect at 90 degrees, then we have a rectangle and a rhombus, which would be a square. If they bisect each other, but they're not congruent, then we have a rhombus. But I think it's easier to just check the slope of these 2 lines right off the bat and see if this is a 90-degree angle, in which case we don't have to check. To see if it is a rhombus, we'll already know that it's, well, it could be a square still, but at least we'll know that we have a rectangle or a square. Plus, it's an easy thing to do. That's the big selling point for me. So what is the slope of this line here? It would be the rise, which is 3 minus 2, over the run, which is 0 minus a minus 4. That's 1/4. Now, if these are perpendicular, the slopes will be the negative reciprocal of each other, which means if the slope of this line is minus 4, it's perpendicular. Let's see what it turns out to be. We've got 2 minus a minus 2. And what's x? We have minus 4 minus a minus 3. Well, this is 2 plus 2. That's 4. This is minus 4 plus 3 is minus 1, which is equivalent to negative 4. So, we have a right angle. Now we have to decide, do we have a rectangle or a square? We could check the length of these two sides. If they're congruent, we have a square. That's probably what I would do. Seems like the easiest thing. I assumed we had a parallelogram. I'm not sure we were supposed to assume that. It's really easy to figure out if we do. These two form a right angle, right? So if we have another right angle here, it'll be immediately apparent that two lines perpendicular to a third line have to be parallel. And it'll turn out that this line has to be parallel to this line also. So really, we've already got the slope for this one. It was minus 4, right? So let's see if the slope of this turns out to be perpendicular to this one, or conversely the same as this. Let's check it. We get minus 1 minus a minus 2, and it's over 1 minus a minus 3. This is already starting to look like we're going to get the answer we want. Minus 1 plus 2 is 1. 1 plus 3, that's 4. Okay, now we're definitely sure. If we weren't supposed to assume it, we just proved it. These two are parallel. I believe this has to be parallel also if these two are, well, heck, it's easy to prove. Yeah, I guess it would still be possible for this line to not be parallel to the segment, so I guess we can check the slope of this one too. Make sure it turns out to be minus 4, which I have a feeling it will be. I can just about do this one in your head. We got 3 minus a minus 1. That's 4. Maybe I better do it. I don't like the way this looks. 3 minus a minus 1. Okay, do it down here. Over 0 minus 1. Okay, that's 4 over minus 1. And that's minus 4. Okay. So we definitely have a parallelogram. Now all we have to do is check and see if the adjacent sides are congruent. Why is that? Well, in a parallelogram, opposite sides are automatically congruent. We could have done that also. Instead of checking slopes, we could have made sure that this side was congruent to this side, and this side was congruent to this side, but we have to use our distance formula a whole bunch. And it seems to me the slope formula, as it doesn't involve any squares, just a nice simple arithmetic ratio, I think is usually easier. But now, I think we're kind of stuck. I don't know. For sure, we could use slopes again, maybe. Remember, if this is, in fact, that's not a bad idea. Suppose we used the slopes of the diagonals. Remember, for a rhombus, and a square is a rhombus, the diagonals are going to be perpendicular to each other. Whereas for a rectangle, no, they won't be perpendicular. And right now, since we have 90-degree angles, we know we have a square or a rectangle. All we have to do is figure out which one. So let's check the slope of these two diagonals. If they turn out to be perpendicular to each other, we have a square. If not, we have a rectangle. And I think it's pretty easy to check the slopes of these two diagonals. For, let's say JK, we get 3 minus 2. Oh, pardon me. I think I did JL first, so we get 2 minus a minus 1 here. It's 3 over minus 4 minus 1. 5. Well, minus 5. That gives us a minus 3/5. Over here, we get 3 minus a minus 2. That's 5. 0 minus a minus 3. So we have negative reciprocals, which means these two diagonals intersect at 90 degrees. So we have a rhombus, at least. But these are all 90-degree angles, which means we have more than a rhombus. We have a square. Well, that's about it.